Today we're actually going to leave geometry behind. We're not going to deal with any more geometry stuff. And interestingly enough, we're going to tackle something new. So this is just a cool map of the different types of math out there. Um, and previously we were kind of dealing with this area, this geometry area, trigonometry. This was our previous wheelhouse. Um, for whatever reason, the powers that be have decided that this other thing needs to get pushed in our geometry class, even though it really doesn't have a whole lot to do with this area here of spaces and structure and trig and triangles and all that stuff. There are a few little applications, but for the most part, we're going to shift gears and go all the way over here to probability, this section over here. Very different field of mathematics. However, it is something we're going to have to cover. So without further ado, that's 21.1. And there's going to be a lot of new terms here and just new ways of thinking about things. So bear with us as we start off. So a few definitions. The first is a set. So a set is any group of things, a collection of distinct objects. Usually sets will be numbers, but they don't have to be. They could be people, they could be shirts in your closet, they could be socks, or it doesn't matter. It's just a collection of things. Each object in that collection we're going to call elements. So there are so many elements in a set. And then finally, we can have empty sets just with no elements, essentially. So in this case, they denote it with a bracket. Sets are denoted with brackets, so therefore, since you have empty brackets, that just means there's no elements in that set. If you define elements under consideration, so for example, if you say all integer numbers or all odd numbers or all primes less than 1,000, no matter how you define it, if you have some kind of definition for that, you can come up with what's called a universal set. So the universal set is all things under the consideration, or it's kind of the broad all possible values set. So that's a specific type of set that we'll be using. And we need to know these terms because we'll be doing some probability within these sets. There's a few other types of things we need to talk about, and it's kind of related to a Venn diagram. You guys should know what a Venn diagram is, right? If you have like, say, these are purple things, and over here these are, t-shirts, and then in the middle are purple t-shirts, right? Things that fit both category. If you have a yellow banana's out here. It's outside of the Venn diagram. So we'll be using Venn diagrams here in a little bit as well. So sets. We'll just run through some examples and practice our notation on this page. So this set, we're defining this set as set A is the set of prime numbers less than 10. So what numbers are in that set? Well, there's 2. 2 is prime. 3, 7, and then we're missing 1 right here, and that's 5. So the number of elements defined as n, right? N of set A is equal to 4, right? There are 4 elements in set A. Set B here, we're going to say, is the set of even natural numbers, so the even whole numbers, whole positive numbers, less than 10. So they have to be even, they have to be less than 10, they have to be whole integers, they have to be greater than 0. So that includes 2, 4, 6, and 8. Right? Notice here, since it says less than 10, 10 isn't less than 10, so therefore it doesn't meet that. And there's 4 elements in that set. Okay, moving on. Set C is the set of natural numbers less than 10 that are multiples of 4. So in this case, we have C is equal to what natural numbers are less than 10, multiples of 4? Well, it's just 4 and 8. So therefore, there are 2 elements in set C. And then finally, the universal set of all natural numbers less than 10, right? The reason why this is our universal set is because that was kind of the pattern of these subsets here, right? They were all looking at natural numbers less than 10, but then this was a specific type of natural number less than 10. This is a specific type. That's a specific type. So all natural numbers less than 10 include 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So therefore, the number of elements in that set, what set? It is 9. But what set is it? It's U, right? The universal set. Cool. We're doing good. So now we're going to combine them. We're going to start thinking about those Venn diagrams here. We can have a subset, right? And I already use this term, and a lot of us use this term in everyday life, right? Like Renner is a subset of my children. And so you can think of this as a Venn diagram. This is the universal set. Every single possible thing under consideration will be inside this universal set, inside this box, right? So we're not considering, things like bananas here or something like that. We're just looking at things in the universal set, and the same universal set that was in the last one, our previous example. So in this case, our universal set is whole natural numbers. And then we have set B. Set B is a subset of that, right? Do you guys remember what set B is? Set B is the even natural numbers less than 10, right? 2, 4, 6, 8. So 2, 4, and 6, 8 all fall within here. If I made this a really big one, I could put, 2, 4, 6, 8. All are within set B. All the other numbers like 1, 3, 7, etc. are going to be outside of set B. But it says set C is a subset, right? And set C, if we recall, is the natural numbers less than 10. They're multiples of 4, so that's 4 and 8. So really, I'm not going to have 4 and 8 here. 4 and 8. Here. 4 and 8, I'll make them red, sure, go inside C, which is already inside B, right? So that's just a way to visualize it. The notation here is with this this little sideways U type thing, and it's a little hard to remember. But one way I think of it is I like to draw like a submarine, right? Here's my submarine. Here's this little propeller. Okay, see, it's a submarine, right? Right. But that's what that sideways U type thing is denoting a subset. So we just went through our example there. We filled this out, right? 1, 3, 5, 7, 9 are all in the universal set. 2 and 6 are in set B, along with 4 and 8, right? But 4 and 8 are also in set C, so therefore they're going there. Okay, a few more. Intersection. So the intersection of sets is the set of all elements that are in both A and B. For those of you in computer science, these are some of your Boolean operators, right? And in this case means that it has to meet both conditions, right, to be in the intersection. The intersection looks like this upside down U type thing, and I think of it as when you get to an intersection, you have streetlights, right? Ta-da! And that's what it looks like. If you have a better way to think about it, feel free. That's just supposed to help you remember. So A and B, well, let's look at A and B again. A is the set of prime numbers less than 10. B is the set of even numbers less than 10, right? So what is both prime and even? Well, there's only one possible thing for that, right? And that is 2, right? 2 is the only even prime, so therefore it's in both set A and in set B. So the intersection of sets A and B contains only the element 2. Okay, next one down. The union of sets A and B represent all elements that are in A or B. Again, our Boolean operator is OR. So if it meets either condition for set A or set B, it'll be included in that union. The union, you can think of it's not a U, but it's kind of represented by this big U shape. So therefore, we can remember union. And in this case, sets A and B. We can refer up here. basically include all of these values, right? 2, 3, 4, 5, 6, 7, and 8. And then finally, the complement of set A just means the inverse, right? So it includes all elements in the universal set that are not in set A. And we write that with a little c, or sometimes we use a tilde mark just to represent kind of the swapping there. So instead of set A here, we're just include everything in the universal set that's not in set A. And again, set A is the prime numbers less than 10, right? So that includes 2, 3, that includes 2, 3, 5, 7, and everything else is in that complement of set A up top. Okay. You understand, Renner? Is it good?
Yep.
Yep. Okay, cool. All right. So here's our example. In the fourth row of a table, draw the Venn. Oh, no, I don't want that. Okay. Do sets always have an intersection that is not the empty set? So is there always an intersection between sets? Think about that. Pause. No, there is not always an empty set, right? If I were to go back to my Venn diagram example, oops. I could have this thing over here and this thing over here. This set is, say, reptiles that walk on 4 legs. This set over here is, animals that, mammals or something like that. There's nothing that meets both conditions, right? So therefore, there is no intersection. Okay. Calculating theoretical probabilities. So we need to know the probability of something to happen, right? And in order to know that, we need to figure out what are all possible things that could happen. So the classic event here is rolling a dice, right? If I roll a dice, what is the probability that the number that comes up on top is a 1? Well, first I need to figure out how many sides are on my dice, right? The classic dice has 6 sides, and each one has a different number, 1, 2, 3, 4, 5, 6. So therefore, there's only one chance for me to get a 1 on that dice, right? Note here that we're going to define probability with a number, right? If you say something is like flipping a coin is another classic example, right? What are the odds that I get heads after I flip a coin? Well, it's 50-50. What do you mean by 50-50? You mean 50%. And how do we write 50%? There's 50%. What is this as a number, as a decimal number? Well, it's 0.5, right? 0.5 for heads, 0.5 for tails. When you add them together, you get 1, right? So therefore, if something is totally impossible, right, it has a probability of 0, right? Well, if something is certain, 100% certain, then it has a probability of 1. So all our probabilities we can list as a decimal between 0 and 1, inclusive. We're going to usually use this theoretical probability of an event A in the sample space S. So this only works for things that are equally probable. So again, the dice works, the coin works. These are fair things, right? So the probability of, say, getting heads, right, or the probability of whatever getting set A is, right, that outcome A, is the number of outcomes in that event. So in this case, if I was to do dice and I just want to get a 1, right? How many sides have 1? Well, it's only one of them. So there'd be 1 outcome there. What are the number of outcomes in the sample space? So the entire sample space, in this case on a 6-sided die, is 6, right? So the number of elements in A versus the number of elements in S here. We'll do some examples here. This first example, you roll a number cube. Event A is rolling a prime number. Event B is rolling an even number. Remember, this is just they mean number cube. They dice, I don't know why. So 1 through 6, right? Our universal set here is numbers 1, 2, 3, 4, 5, 6, right? So the number of elements in that set is 6. So we want to calculate the probability of A, which is a prime number. So how many elements in that universal set are prime? Well, there's 3 of them, right? So what are the odds? It's simply the number of elements in the A, right, over the number of elements in the universal set, or 3 over 6, or 1/2. So it's a 50-50 chance that when you roll a dice, you'll get a prime number. Event B is rolling an even number, right? The probability of B would also be 50%. But it gets a little more interesting when you start talking about the union here, right? Remember the union? You can think of the union as the big U here, these 2 things overlapping, or the OR function, anything that's in either one of those. So the union of A and B has how many elements? Well, we just list off the elements here. We say, okay, it can be 2, it can be a 3, it can be a 4, it can be 5, it can be a 6, right? So the number of elements in that union is 5. So therefore, the probability of getting a number that is in the union of A and B, right, is equal to the number of elements in the union of A and B over the number of elements in the universal set, or 5 over 6. A few more. The intersection. Remember, what elements are in both A and B? Well, there's only one element. That's the value 2. So again, it is one element, right? 1 over the total number of 6. What is the complement of A? Well, the complement of A is the elements 1, 4, and 6. Notice here we can do kind of a shortcut with the complement, and we'll get to that here in a second. But we can do simply the complement is going to be equal to 1 minus the set itself, right? The probability of that set. In this case, it's also 1/2. Okay, so those are pretty good examples. We'll do one more example here. Your grocery basket contains 1 bag of each of the following items. So these aren't numbers; these are just things, and the elements in here are vegetables. Oranges, green apples, green grapes, green broccoli, white cauliflower, orange carrots, and green spinach. You're getting ready to transfer your items from your cart to the conveyor belt for checkout. Event A is picking a bag containing a vegetable fruit. Event B is picking a bag containing a green food first. All bags have an equal chance of being picked first. Okay, so event A is a vegetable. B is green, right? So we need to start thinking about these sorts of things. So set S, this is the universal set, right? Includes the orange, the apple, the grape, the broccoli, cauliflower, carrot, spinach. So the number of elements, 1, 2, 3, 4, 5, 6, 7. We can just count those. Okay. Set A, right? What elements are in set A? A is the vegetables, right? So which ones are vegetables? Broccoli, cauliflower, carrot, spinach. Those are all vegetables, so therefore the number of elements are 4. The probability of set A, the probability of event A, sorry, is the number of elements in set A over the number of universal elements, which in this case is 4 over 7. The union of B, right? These are things, the OR, is it an A or B? Broccoli, cauliflower, carrot, spinach, plus all of the things in B, which are green. So what is green that isn't a thing? Well, that's green apples and green grapes. So include the apples and the grapes. So the number of elements in the union of A and B is equal to 6. So the probability, therefore, is 6 over 7. Okay, what about the intersection? Remember, this one is and, right? It has to be both A and B. So let's think about this one for a second. How many things are both vegetables and green? Well, this is a shorter list. We have spinach, we have broccoli, and that's it. Right? So there's only 2 elements, spinach, broccoli, 2 elements there. So therefore, the probability of the intersection of A and B is 2 over 7. And then finally, the last one is the probability of the complement of event A, right? The complement of event A is picking a vegetable first. So how many of these things are not vegetables? Well, that includes oranges, apples, grapes, and so there's 3 things. Can you count to 3, Renner? Can you go 1, 2, 3? 3, good. So 3 out of 7. Hooray! Of note here, we left these as fractions, but they can definitely be expressed as decimals, right? You can do 6 divided by 7 on a calculator and it gives you some crazy decimal. Okay. In example 1b, what is greater? The probability of A union B or the probability of A intersection B? The intersection of A and B or the union of A and B. Do you think the result is true in general? Explain. Pause. Book your book. Yes, it is generally true. The union includes all elements, whereas the other one, the intersection, just includes some things. It is possible for them to be equal. However, the union will always contain at least as many things as the intersection. Okay. The numbers 1 through 30 are written on slips of paper and then placed in a hat. Students draw a slip to determine the order in which they will give an oral report. Event A is being one of the first 10 students to give their report. Event B is picking a multiple of 6. If you pick first, calculate each of the indicated probabilities. Okay, so go ahead and do these ones real quick. Pause. And try hard on this, please. Actually put some effort in and think about it and reread it. Okay, so the probability of event A being one of the first 10 out of 30 is 1/3. The probability of A union B, or the union of A and B, right, is not only the first 10, right, but also being a multiple of 6, right? So it includes the first 10, and then 12, 18, 24, 30. So therefore, the number of elements there is 14, so it's 14 out of 30 is the total percentage, or odd. The probability of A intersection B, right? The only value that's both in A and B is 6, so therefore it's 1 out of 30. And then finally, the complement of event A, right? Not being one of the first 10 means it's one of the other 20, so therefore it's 20 out of 30, or 2/3. Okay, that was just a warm-up for probability stuff. We'll actually cover more of this first section later. Have a good day.